everyone, how are you doing? All are doing good? That's great. I'm Mahesh, your physics teacher, and you're watching me on SMR Online Physics. This is a continuation of the series on the topic of refraction of light. In the last class, I discussed about critical angle. If you haven't watched it, please watch it and then come back to this video. It will enhance your understanding and learning for better. If you are new to this channel, do subscribe the channel SMR Online Physics for more interesting videos on the topics of physics. So don't forget to like, share and subscribe my channel. And here we go. Today's topic will be something more fascinating which I promised in my last class. Today I'm going to discuss about total internal reflection. Alright, here we go. The topic for today's class, total internal reflection. Please mind it. I said this is a part of the series on the topic of refraction of light. And I wasn't wrong in saying that, but at the same time I'm right here too. This is not total internal refraction, it is total internal reflection. Okay? See what exactly it means like. Total internal reflection. It's like bouncing off. We have definitely learned about what is reflection of light. Then what is total internal reflection, and is it really different from reflection of light which is done primarily by any opaque surface, or to say the mirrors and the spherical mirrors, as we already discussed in our previous classes. Alright, so let me tell you what is the difference. Here actually both the mediums in consideration are transparent mediums, and here and still the light does not actually refract into the other medium, but rather it bounces off the interface of the two media, so that it almost behaves like an absolute plane mirror. Okay, so why it happens like? So that's why I said please be clear about the term called critical angle. So let me draw you a diagram. This straight line indicates the interface, and my dear, the total internal reflection phenomena is observed when we consider rarer and denser mediums, which is very necessary, and much more necessary is this will only happen when a ray of light propagates from denser to rarer media, but not for every angle of incidence. It will be only observed for that chosen pair of media. I mean to say, if you are doing glass-air experiment, so for glass-air interface, there is a unique angle of incidence which is called as critical angle of incidence. If you're trying to do it for example, water with respect to air, for that pair of media, the critical angle of incidence will vary. Alright? So for every pair of media, there is a different critical angle of incidence. So when does this phenomenon exactly happen? It happens when a ray of light is incident from denser medium to the rarer medium, and the angle of incidence I is definitely greater than the critical angle of incidence for this chosen pair of media. This, what I put in the box, is the important and the only important condition. So definitely denser to rarer medium, the direction of propagation of light, but more importantly, I should be greater than the critical angle of incidence. In such a case, the ray of light, instead of going straighter, or instead of, as you expect, bending away from the normal, nothing happens. So the interface behaves like an excellent reflector, and this entire energy or intensity of the light which strikes the interface bounces off 100%. Wow! The transparent interface is behaving like a super smooth mirror, much better than a plane mirror, I can say. 100% of light's energy or intensity is bounced off by the interface and creating exactly equal angle. That is called equal angle of reflection in that case. So 100% reflection takes place. This phenomena, my dear, is called as total internal reflection of light. Hope I'm very clear about that. Right? Okay. So this is what exactly happens, and the other conditions we definitely know. If the angle of incidence would have been lesser than the critical angle of incidence, then the ray of light would have been refracted into the rarer medium as we generally expect. If it would have been exactly at the critical angle of incidence, then you would have found the angle of refraction created would have been exactly 90 degrees. So if I is greater than theta of C, then you find this phenomena taking place. So it has wonderful, plentiful of uses in day-to-day life in various optical instruments. So let me talk about one by one in details. All right? So now I'd like to discuss in details about the phenomena of total internal reflection in various shaped prisms. Okay? Regarding the behavior of prisms with respect to light, I have already discussed in my previous video. If you haven't watched it, please watch it and then definitely attend this video. So in prisms, we'll talk about three varieties of prisms. Okay? One is the right angled isosceles prism. The right angled isosceles prism is also familiarly known as 45 degrees, 90 degrees and 45 degrees. This is one prism we are about to discuss. Then we will discuss about what happens in a equilateral prism. Okay? What happens in equilateral prism? As the name itself suggests, all the three angles will be exactly equal to 60 degrees each. So it is 60, 60, 60. And the third one is a simple right angled prism. A right angled prism. Here one of the angles is 30, the other is 60, the other is 90. So it's like a 30, 60, 90 prism. Okay, so let's get started with the first type. Whether total internal reflection is possible in the right angled isosceles prism or not, and what are its various applications in modern tools like periscopes, binoculars and many types of cameras and projectors. Alright, it's an interesting phenomenon. Let's enjoy it. Come on. So let me rub this off. You have noted it down, I'm sure. So let me get on with the first one, that is called the right angled isosceles prisms. Right angled isosceles prism we are about to talk. What is the angles here I told you here? My dear, it is also famously called 45, 90, 45 degree prism. Okay, so let me first of all discuss the case 1. Okay, let me draw you a beautiful prism diagram which is extremely crucial to understand. Yes, yes and yes. Come on, this is it. So here I mark the angles. This is my 90 degrees, this is your 45, this is another 45. This is what I meant by saying here. So let me name it out quickly. This is P, Q, R. So what will happen to a ray of light? Here, my dear, you need to recall that I'm talking about air glass medium. So in my previous class also I discussed the critical angle for glass air medium is around 42 degrees. And total internal reflection will take place if the angle of incidence is greater than 42 degrees. So what happens to a ray of light which is incident on the surface PQ, which is also the perpendicular side of the prism? If a ray of light is incident upon this surface of the prism, you can see that it is striking at 90 degrees. So just goes in straight, normal incidence case. So this is your 90 degrees, right? So 90, 45, this has to be your 45 degrees. We will definitely deal with small amount of geometry. Now you observe closely at the other face, that is PR, this ray of light is actually striking at an angle of incidence of 45 degrees. That's amazing, that's beautiful. 45, that is greater than 42. So if the angle of incidence is greater than the critical angle, then this ray of light won't be transmitted out. Please mind it, this is also transparent surface. You exactly expected refraction to be happening, but no, it bounces back into the same medium. 100% reflection takes place, making an equal angle of 45 degrees, which is a must here. So this is your another 45 coming up, 45, 45, so this has to be at 90 degrees. So the ray of light just transmits through the base of the prism QR. So if another ray of light you visualize here, a parallel ray of light, exactly the same thing would have taken place. Just bounces off and there it goes. That's it. This is what I meant by saying total internal reflection taking place from a right-angled isosceles prism. This idea of designing the prism is extremely crucial in excellent modernized periscopes. It finds its use in periscopes, and I'll definitely discuss about the wonderful applications of total internal reflection in one of my next videos. Okay, let us first of all discuss in details what exactly happens over here. I hope I'm very correct in terms of all the angles, right? Please, come on. So in this diagram, you could easily see that the angle of deviation, by what angle the entire ray of light has been completely deviated. This ray of light comes from this direction, you just produce it forward. Yes, you can clearly see that angle, I suppose. This is your emergent ray. If you produce it backward, you will find that the angle of deviation, the deviation of the ray of light suffered in this particular position is equal to 90 degrees, right? Okay, let's move on to the second possible case of this prism. Right. So what if the ray of light strikes the other surface of this prism? Alright, so let me show you something like that. Okay, the same prism I'm talking about. I just oriented it in a different manner. This is your 90 degrees. This is your 45 degrees. This is your 45 degrees. Alright, so let us say this is PQR. The same prism, my dear, I just oriented in a different way. So now, if the ray of light is incident upon this prism through the bottom half, that is PQ, or if you just check it out, it is your hypotenuse of this prism, then what would have happened? A ray of light striking from this, suppose here. Okay, so definitely is going at 90, you can see that angle. So 90, 45, this has to be a 45. So if I draw a normal, the things become very clear to visualize. Let me draw a normal, right? So if this is 45, then definitely this is also 45. Yes, bingo. It's greater than 42. So the ray of light won't be refracted out of the surface, rather it will bounce off, making an angle of 45. So the refracted, or I should say reflected ray of light will be in this particular direction. This is 45. This has to be 45. So now it strikes over there. So this has definitely a choice of 45. Again, you try to visualize the normal over here. Again, to the second surface QR, again the angle of incidence is greater than the critical angle of incidence, so the ray of light bounces off from the surface. This is it. It bounces out, creating, this is 45, this is your 90, this is another 45. I hope it's absolutely clear. Alright, so in this fashion what would happen is, suppose you have an object over here lying. If this is your object, I hope you can see that right at the bottom of the screen, and another ray of light comes from the base of the object straight up and strikes, the conditions are exactly the same. I think you got it. So it's going to bounce off there, and this ray is again going to get reflected off, and there you go. So this is your head, this is your feet, so everything gets inverted. So this is your head now, this is your feet. So if this was the object, that's your image. So let me draw it a bit up so that's clearly visible to you. This is what it would have happened. Head, feet. Is that clear? That's how the total internal reflection would have taken place in case of a right-angled isosceles prism if the ray of light could have struck from the surface PR, that is the hypotenuse of the prism. Alright, great. This prism's usage is mostly done in binoculars or in certain types of cameras too. Alright, so let's move on to the next possibility of this specialized prism. I think I can rub it off. Clear? Now I'd like to talk about the third usage of this specialized prism. Alright, so the third usage, C. The orientation of the prism will look absolutely the same. Let me draw a bigger prism. Yes, that's it. This is your angle of 90, and still I'm using the same prism. This is your 45, this is your 45. This orientation is a very highly useful to erect an inverted image. So it's widely used in projectors. Wonderful, isn't it? Right. So what happens here is, suppose there is an object which is already kept inverted, and I need to make an erect image as the projectors do, right? So here from the base, suppose a ray of light is incident on the face PQ, and here the angle of incidence, after drawing the normal, you can easily visualize that this angle of incidence I is lesser than the critical angle of incidence. So since it is lesser than the critical angle of incidence, the ray of light won't be bouncing off, won't be reflecting, and won't be going straight for sure. So definitely it would be refracted. So instead of going straighter, it should be bending towards the normal. So I mean to say something like this. Not an exactly beautiful diagram. Okay, let me just erase it. Alright, something like this. Okay, something like this. You understand what I mean to say. So when it refracts back and it strikes the base of the prism, that is the surface QR. This is your 45, correct. Now this angle of incidence is greater. This angle of incidence is greater than the critical angle of incidence. That is the point to be noted here. Now because of that, it will be bouncing the light ray off. As it bounces off the light ray, these both angles are absolutely equal. Now the normal, it can be drawn this way. So it won't be really bending towards the normal, it is bending away from the normal. So you'll be finding it goes parallelly out. It goes parallelly out of it and comes out parallel to the base of the prism. So similarly, if a ray of light comes from the head of it, the same arguments follow. It bends, and the angle of incidence on the surface is greater than the critical angle of incidence. So hence you find it bounces off. This is where the total internal reflection is taking place, my dear. and now again it retraces out parallelly. So as it retraces out parallelly, observe it. This is the head, this is the foot. So this foot ray came over here, and this ray of light coming from the head goes up there. So now the entire inverted image has been turned into an erect image. This is excellent usage of this prism in wonderful machines called projectors. In real life projectors, this is the technique they utilize. Hope you're enjoying this usage of total internal reflection. Okay, come on. Now, let me discuss the phenomena of T.I.R, total internal reflection, in the second type of the prism. What was the second type, my dear? It's an equilateral prism. In equilateral prism, what are the possibilities? Let us quickly check it out. It's highly useful for the students of ICSE 10th class without any doubt. It's a part of your syllabus and definitely acts as a very good foundation course for all the other students. Great. I hope you're enjoying it. Equilateral prism, what was the angles? I was talking about all the three angles being equal to 60 degrees each. Very, very common prism which we have discussed in our previous classes also. But what about the total internal reflection phenomena? So let me draw a good sized equilateral prism. Am I getting it right? Okay, good. This is your 60 degrees, this is P, this is 60 degrees, this is Q, this is 60 degrees, this is R. Alright, all the 60s. Now, under what condition you would find a total internal reflection in such a type of a prism? Suppose a ray of light is incident, because all the angles are equal, right? So a ray of light is incident in such a way that is exactly striking the surface at an angle of 90 degrees. It's a normal incidence case. So this ray of light will be transmitted straight through it. Observe it. So when it's going straight through, this is also your 90, right? If this is your 90, this is 60, 90, 60 is 150. So you are left with a choice of 30 degrees. There we go. There we go. Now look at the second phase of this prism. You draw the normal quickly, and this angle of incidence has to be 60 degrees. Means the angle of incidence is much greater than the critical angle for glass air interface, where the critical angle for such pair was around 42 degrees. So it's hitting at 60 degrees. So the ray of light won't be transmitting through, rather it should bounce off. It should bounce off in such a way. In what way it should bounce off? This is 60, then you should get 30, this is another 60. So it should be bouncing off something like this. Yes, something like this. If my diagram is very clear, this has to be your 60, this has to be your 30, 60, 30 is 90, so you're left with no choice, but this has to be at 90. That's it. So it just comes and strikes and moves out. I get your point clear? Okay, that's it. That is how the total internal reflection exactly takes place in an equilateral prism. So if you observe the angle of deviation, so definitely if you observe this diagram closely, it's very easy to calculate the angle of deviation suffered by this ray of light. This ray of light came along this direction, so just produce it forward and use some geometry of the straight line. This is the straight line created, 60, 60, this is 30, so this is another 30. So the total angle of deviation created is around 60 degrees. That is how the ray of light actually deviates away from this kind of a prism. Beautiful. If you can see over here too, if a ray of light comes over here and suppose it strikes the base of the prism itself, so what would have happened exactly? This is what? This is your 90. So it would have gone straight through it. As it goes straight through it, you can observe that this is your normal, this is your 90, this is your 30, my dear, this is your 60. Again, the angle of incidence is greater than critical angle of incidence. Alright? So in such a case, definitely it bounces off at 60. So as it bounces off, this is your another 60 there, this is your another 30. So you can easily observe this ray of light going straight through it. The original intended direction, but this is the actual direction of the reflected ray of light. So another case of total internal reflection. So the total angle of deviation, this is another 30. So this is the total angle of deviation, which is equal to 60 degrees. This is the beauty of an equilateral prism. It can deviate the light ray through 60 degrees. I hope you're enjoying the class, right? Come on, note it down. So now let us move into the third kind of a prism, alright? The third kind was right angle prism. Whatever the possibilities were there for the first two types of prisms, I have discussed in details. Now let us go into right angled prism. What was the right angled prism, my dear? The angles are 30, 90, 60. So is there your 30, 60, 90 prism, you can say like. Alright. So let us see the first possibility of it. Are we ready for that? Come on. So you get, there has to be an angle of 90 degrees. Let me get it straight up. Get it straight. Get your diagrams neat and clean. That's critically important. And it looks something like this. So this is your 90 degrees. This is your 60 degrees. This is your 30 degree prism. So let us name it out. PQR. So is there any possibility of total internal reflection in such a type of a prism? That's the point in question. So if a ray of light is incident through the base surface adjacent to the 60 degree angle and strikes over here, let us see what happens. A ray of light passing right through at normal incidence. So this is your 90, the symbol is enough, 90, 60. This is your 30, right. So get your normal and this interface. Once your normal is done, now you're very sure the angle of incidence is 60 degrees. Again, as I've been repeating many times, this is greater than the critical angle. So the ray of light does not transmit at all through the phase PR. Rather, it will reflect the light as if it's a perfect plane mirror. So it reflects the light off. Yes, this has to be your 60 degrees. Then this has to be your 30. Observe these angles closely. 30, 30. Only 60 done. You're left with 120 over there. So now if you get your normal right, yes, so it means it is 90. So you're left with one more 30. Because 90 plus 30, it should be equal to 120 degrees. So now the angle of incidence is lesser than the critical angle of incidence. So my dear, this ray of light won't suffer total internal reflection. Rather, it will undergo very ordinary refraction of light. So this ray of light, instead of going straighter, don't forget, denser to rarer medium. So it should be now bending away from the normal, creating an angle of refraction. This is what would have happened to a ray of light in case of the right angle prism if the ray of light hits you at the base. And that is how it totally internally reflects, again refracts. So this is a small possibility which is possible in this case of prism, but not every time you will be lucky enough to witness this total internal reflection in such a type of a prism, as I show you over here. This is your 90, this is your 60, this is your 30. You can always definitely experiment it through. If a ray of light is incident from this surface PQ rather than QR, if a ray of light is incident something like this, observe this. So definitely it is hitting you at 90 degrees. 90, 30 is 120. 120, this is your 60. So now you see that the angle of incidence created at this phase is actually lesser than the required critical angle. That is only 30 degrees. So it will be bouncing off. Sorry, it won't be bouncing off. No reflection is possible. Rather, this ray of light would be refracted through denser to rarer, so it will be bending away from the normal. That's it. So be very careful about that angle of incidence. Okay, let me just rub it off and show you that for this prism, if the ray of light would have strike upon, this is your 30 as I say, this is your 90 as I say, this is your, what is that, 60 degrees, and this is your PQR. So we have seen through both the surfaces, PQ and QR. What would have happened to the ray of light if it would have actually strike upon this hypotenuse of this right angle triangle? Something like this. A ray of light striking here. As it strikes here, you'll see that it is 90, this is your 90. So 90, 30, 120. So this has to be your 60. So this is perpendicular. So draw a normal here. This is only 30 degrees. So again you find that the angle of incidence at this phase is 30 degrees, which is lesser than the critical angle. So the ray of light won't be bouncing off. Means no total internal reflection is possible. Rather, refraction is possible, bending away from the normal. Are you getting the point here? Are you getting the point here? Is that clear to all of you? Great. Come on, please note it down. So now let us move into one exceptional case regarding the right angled prism. What is that? What is that exception I'm talking about? See that. You have your prism, the same one my dear, which I'm talking about. This is your 90 degrees, this is your 30 degrees, this is your 60 degrees. Very, very important and very useful. Okay, they have got tremendous uses. I'm going to discuss about this phenomena, total internal reflection, the uses. Don't miss it out in my next video class, right? That is wonderful. Now what was the exception in this case is that if the ray of light would have struck really through PR, as I just showed you, and that ray of light goes and hits the perpendicular, that is PQ, rather than hitting upon the PQ, if it hits upon at the base of the prism QR, what would have exactly taken place? Is there any possibility of total internal reflection? Just put it narrow down. Yes, this is what I mean to say. This is hitting at 90s. So if it is 90 there, 90 and 60 is 150. So this is going to be your 30. So this is your normal. And if that is 30, this is your 60. Yeah, that's a bingo. The angle of incidence is greater than critical angle, that is 42. So this ray of light won't be passing out. It will be actually reflecting 100%. So the reflection will take place something like this. So let us first of all perfect these angles. This is your 60, this is your 30, there you see 90 there, 90, 30 is 120, this has to be your 60. Now my dear, at this phase PQ, the angle of incidence is only 30 degrees, which you have easily understood is lesser than critical angle. So rather than bouncing off, the ray of light going from denser to rarer would be refracting away from the normal. Alright? I hope I was very clear in my discussion on this topic of various kinds of prisms and this wonderful phenomena called total internal reflection. Hope I'm helping you in understanding these lovely topics of physics. Okay? Please stay safe, stay healthy, study well, keep rocking, and keep the motto in your head very clear. Physics is all about having fun. It's all about imagination, very small bit of mathematics. See you again in my next video class. Do not forget to like, share and subscribe my channel SMR Online Physics. Bye. See you again.